In this video, I am going to explain the theorem. Let me read the statement. If V and W are of dimension M and N respectively over F, then homomorphism of V, W is of dimension Mn over F. Okay, so here what they are given in the statement, they are given two vector spaces, okay, capital V and capital W, and they are saying that the dimension of capital V is M and the dimension of capital W is N, okay, over the field F, and they are asking us to find the homomorphism of V, W is of dimension Mn over the field F. Okay, so here they are talking about dimension, right? So you need to know what is meant by dimension. Okay, so that you have a definition for dimension. Let's have a look at that. If V is a vector space, okay, here you have a vector space V and over the field F, the number of elements in any basis of V over F is called dimension of V over F. Okay, so what is meant by dimension of V? Number of elements in any basis of V. So here rise a question, what is meant by basis, right? Here is a question, what is meant by basis? So let me tell you what is meant by basis. So you can see the definition of basis here. Consider a subset of a vector space V. Okay, so here the vector space, the subset S of a vector space is called the basis of V if S contains linearly independent elements and V equal to L of S. This V is equal to L of S is not necessary to prove this theorem, so I don't want to get into that. Okay, so we need linearly independent elements. This if you want to say subset S as a basis of V if S contains linearly independent elements, this is what necessary for this proof, so I will talk about that in this video. Okay, so here is a question, what is meant by independent elements, right? So here I have an answer for that. Here is another definition. If V1, V2, etc., Vn are linearly independent, if you want to say these vectors as linearly independent over the field F, if there exists some of the scalars are lambda 1, lambda 2, etc., lambda n belongs to F, such that it is in this format, okay, lambda 1 v1, using scalars and vectors you will write like this, lambda 1 v1 plus lambda 2 v2 plus etc. lambda n vn is equal to 0, implies the values of lambda 1, lambda 2, etc., all the scalars will be 0. If it is like that, then you can say these vectors are linearly independent. So these are the definitions that you are going to apply or use in the proof of the theorem. I am going to explain you now. Okay, so let's start proving this theorem. Okay, in the first, what you are going to do is you are going to say homomorphism of V, W is of dimension Mn. Okay, so for that you have to, what you are going to do is you are going to take one element from homomorphism of V, W in the first part of the proof. Okay, so that name of the element is Tij. So what you are going to do is, in the first part you will say this Tij is an element of homomorphism. Okay, or this Tij is a homomorphism. Okay, that is what you are going to say. Okay, so in the next part you will say that Tij form a basis. Okay, and then you will say this basis consists Mn elements of, let me see that once. Okay. And in the third part you will say Mn element, there will be Mn elements in Tij and this Tij is linearly independent. That is what you will do in the last part. So here I am dividing this proof in 3 parts. Okay, in the first part what will you do? You will tell Tij is a homomorphism. And the second part you will say this Tij is forming a basis. and in the third part you will say there is mn elements and this mn elements are linearly independent. This is what you are going to prove in this theorem. Okay, so let's start from the first line of the proof. Proof. Let v1, v2, etc. vm be the basis of v over f. Okay, you are taking some of the basis from the vector space v, and you are taking some of the basis from vector space w. Okay, so let v1, v2, etc. vm be the basis of capital V over f, w1, w2, etc. wn be the basis of w over the field f. Okay, now if v belongs to capital V means, okay, what's mean by that? If you are taking one element from the vector space capital V, the elements in the vector space capital V will be in this form. That is what is given. Capital V, you are taking like that. Okay, you are assuming like that to prove this theorem. So small v is equal, the elements in this vector space capital V will be in this format. Lambda 1 v1 plus lambda 2 v2 plus etc. plus lambda m vm, where this lambda 1, lambda 2, etc. lambda m are what? They are uniquely determined elements of f. They are scalars, so obviously they are the elements of f field, right? Okay, so here they are unique elements. That is what we have written here. Okay, unique elements mean what? It means the values of this lambda 1, lambda 2, lambda are different. They are not same. That is what the meaning of this sentence. Okay, so let me turn to the next page. Okay, so here you are going to say, you are going to define a mapping. Only if there is a mapping, then you can say that Tij is a what? Tij is a homomorphism. Okay, to say something as a homomorphism, we need a mapping. That is the most important thing, right? That is the first and foremost thing that you can do to say something as a homomorphism. So here you are going to define Tij from V to W, vector space V to W by V Tij is equal to lambda I Wj, where I is equal to 1 to etc. m and j is equal to 1 to etc. and this is how you are defining. Okay, nowhere is there, nowhere is like this. You are defining. And take Vk Tij is equal to 0 if I not equal to k and Wj if I equal to k. Okay, you are defining like this. You will use this when you prove Tij is a homomorphism. Okay, so you should know what is mean by this. If the suffix in the what is the suffix of V? K, right? Right. So if this value, the suffix of k, whatever the value might be, okay. So here if in the place of k, there will be some other values. Okay, whatever. If this value, this k value and here Tij in Tij in ith value, okay. K's and I value are not equal, then you have to put 0. If they are equal, for example, Vi, Tij, if it is like that, then what you have to put? Wj. That is what meaning. Wj if I equal to k. Okay. So here we are going to prove Tij is a homomorphism. To prove Tij is a homomorphism, we have to prove these two conditions. Okay. So before getting into that, you have to know all these things. What you are going to prove. Okay. Only then you don't get any confusions when proving that Tij is a homomorphism. Okay, so first you have to write these two conditions. Okay, this is what you are going to prove. So to prove this, you need V and W, right? So you are taking that is what you are writing here. Let V and W belongs to capital V. You are taking two elements from where? Capital V. Both are from capital V. Okay, note this. Then small v is equal to what? I already told you the elements in the vector space capital V will be in this format, right? So small v is equal to lambda 1 v1 plus lambda 2 v2. The vector space V is of dimension m, right? So that is why here you are ending this term with lambda m vm. Similarly, W is also an element from the vector space capital V, so that you are ending this term also with m, right? Because vector space V of dimension m. Okay, is that clear? Now you are going to prove this, right? You are going to consider this first. you will prove this first condition first. So what you are doing, you should consider this first, and using this you will prove this. So here what you are doing is v plus w, right? Firstly we are finding the value of v plus w. So v plus w is equal to, write the value of v and write the value of w. Then from this you will get this lambda 1 plus mu 1 into v1. v1 is common in both the first terms, right? Similarly, you are writing, you will get this value. Now you are finding v plus w into tij. Consider this left hand side, that is what this. So just here you are multiplying tij in each terms. Okay, that is how you got this. Now you are applying this. What? You are applying this condition here. Okay, you are applying this condition here. So here look at this. Okay, v1 tij. So here in the place of k, here we have 1. Here in the place of I, we have I. Anyways, these two values are different. Here is 1, here is I. So both are different, right? If it is different, what you have to put? 0. So that is why here you are putting 0. In between you will have an I term, okay? So in the ith term only you get the value. All other terms will become 0. Okay? So you will get this, and after that just multiply lambda I wj plus mu I wj. So you get this, and after that write lambda I as it is. In the place of wj you are going to substitute the value this. Substitute this value. So here you are not putting k, here you will put I. The place of wj you are substituting. So this value and this value, sorry, this is not visible to you, right? Okay, so here, so this is you are substituting in the place of wj you are substituting this, so that this value and this value should be equal, right? Should be equal, then only you can put wj. So here the place of wj you are substituting. So here in the place of, here both are same, right? You have to put like that. This two should be equal. So that is why lambda vi tij plus mu I, here vi tij. Then this can be written as, consider this, concentrate on this. This is lambda I. This is in this format. Okay, you are going to apply this to this. So here have a look at this lambda I wj. Here is also lambda I, right? Right? It is also lambda I. Consider these two as wj. So this is also lambda I wj format. If it is lambda I wj format, then you have to write like this, right? So that is how you are writing v tij plus w tij. Okay. Now you have proved the first condition of homomorphism. Similarly, prove for the second condition. You can have a look at this. You could understand. So that the two conditions are satisfied. So you can say Tij is a homomorphism. Hence Tij belongs to homomorphism of v comma w. You proved, okay. Now you are going to say that Tij form a basis of homomorphism of v comma. It form a basis. Then you will say that there is mn elements, and these mn elements are linearly independent. This is what you are going to prove in this theorem. So to prove that Tij form a basis of homomorphism of v comma w over the field F, we have to prove vis not equal to vis. This is what the condition you are going to prove here. So for that, to prove this, you need S, right? So that is why you are taking S from homomorphism of v comma w, and you are saying v1 of S. You are considering, okay, the v1 of S will be in this format, okay, because we need vi of S. So to find that, you are considering first v1 of S. So v1 of S equal to alpha 1 on w1 plus alpha 1 to w2 plus etc. plus alpha 1 and w1 for alpha 1 and alpha 1 to etc. or belongs to F, right? So this is v1 S term. So what will be vis term? Vis term. So in general you write the place of 1, here you will put I. Okay, so alpha I1 W1 plus alpha I2 W2 etc. alpha n W, where I is equal to 1, 2, 3 etc. M. Okay. Now let's consider S naught. So we find VIS. Now you have to find this, right? Right. So okay. So here you are considering the value for S naught. Let S naught equal to alpha 11 T11 plus alpha 12 T12 plus etc. plus alpha 1n T1n. Then you have to write like this. In the middle you have to write ith term, and in the last you have to write the mth term. Now you find VIS naught. Just multiply VI with this. Just copy it down. Okay. Now that is equal to VI of all the other terms will become 0. Only ith term will be there. Okay. So that is why I am writing ith term. Okay. Okay. So here that is equal to just multiply. That is how you have written. So in the place of VITI1, you put W1. These two are equal, right? So you can put with write W1 this value plus alpha I2 W this value 2, right? You can write like this. So this is the value of what? VIS. Okay, VIS. So VIS, okay, this and this look similar, right? So you can put VIS not equal to VIS. So from this you get S not equal to S. So here S not is linearly independent. This is linearly independent, right? Linearly independent. So here you can say if S not equal to S means S not is linearly independent. Therefore S must be linearly independent, because we got S not equal to S, right? So S also linearly must be of linear combination. Therefore from this you can say Tij form a basis of homomorphism of V comma W over the field F. So next we are going to prove there is Mn elements, and this Mn elements of Tij is linearly independent. This is what we are going to prove next. So for that you consider this term. Okay, beta. Here just write as it is, but in the place of alpha here you put beta. That is the only difference you are going to make. So just copy down and put at last you put equal to 0. Okay, now that is you find Vk. Just multiply this term with Vk so that you get Vk of, just copy down this equal to, put 0. Now you here all the values get 0. Only k terms will remain. So just copy down the k terms and just multiply this in the next step. You will get this. So here for this you can put W1. For this you can put W2. For this you can put Wn etc. W1. So from what you are writing all these things? From this. Okay. From this plays a key role. Okay, so you are writing like that. Now what you are doing, just writing all the terms you have got, and then since this W1 W2 are linearly independent. What is mean by that? W1 W2, the value of W1 W2 W or all are what? 0. Okay, so that is what, then you get beta k1 equal to 0, beta k2 is equal to 0, etc. beta kn equal to 0. So from this you can write beta kj. Here 1, 2, 3 in the you are writing in general. Beta kj equal to 0, j equal to 1, 2, 3 etc. up to n. So here in the place of k you are putting I, y. Why you are putting? Because you have written here I is equal to k, right? So from here you are writing like that. Beta in the place of k you are putting I. Beta ij equal to 0, where I equal to 1, 2, 3 etc. m and j is equal to 1, 2, 3 etc. n. So thus Mn elements of Tij is linearly independent. If you get 0, then it is linearly independent, right? So here what you are writing, Mn elements of Tij is linearly independent over the field F. Thus they form a basis of homomorphism of V comma W. Therefore what you can say? Homomorphism of V comma W is of dimension Mn over the field F. So here comes the proof end. Here the proof ends. Okay, with this result. Okay, if you have any doubts, please ask me. I will clarify your doubts. Okay.